streaming. There we go. Dijkstra's algorithm is also out of the scope of exam 2. All right, so this is the practice test for you guys, and this is the actual exam 2 last semester. So we'll go ahead and skip most of the things at the beginning. It's open book, open notes, that sort of thing. Same as basically every test, or the first test. So here's question number 1. So question number 1 has to do with counting and probabilities. So we'll go ahead and zoom in a little bit. So question number 1 says, an experiment has 5 trials. Each trial involves tossing a coin and observing how it lands. An observer counts that in 1,000 experiments, 623 ends up with 2 heads and 3 tails. Assuming the observed experiments are representative of the behavior of the coin, what are the chances of tossing a coin once and having to land on a head? Show your derivation and explanations. The final answer can be a closed form equation with the probability variable on one side of the equation by itself, so there's no need to actually compute the value. So I just want to know how you're reasoning this out, okay, using mathematics. And also using binomial distribution. This is clearly related to binomial distribution. So the numbers, as it turns out, this 623 observations is actually impossible. So we'll just say, instead of 623, we'll just say that it is x. So now, your equation, your solution, only has to be expressed in terms of x, 1,000, and using binomial distribution as your tool to figure out, the actual chances of, tossing a single coin one time. All right. So are there any questions about the little change here? No questions? All right.
Sorry. X, you mean X ends up having 2 heads and 3 tails, so that means it's one experiment out of and 5 trials become.
It would be out of 1,000 experiments, many of those 1,000 experiments ends up with 2 heads and 3 tails. Okay, is that okay? All right, so I'll make it clear. So X experiments. Okay, so that makes it clear. So we have 1,000 experiments altogether. Each experiment has 5 trials. We're basically tossing a coin 5 times for each experiment. Out of 1,000 experiments, X experiments end up with 2 heads and 3 tails, ordered independent. Okay, so we don't care about the ordering. So now we want to find the closed form equation with the probability on one side of the equation, the probability being tossing a single coin once and having to land on a head. Okay, so how do we formulate this? So this has to do with binomial distribution. And we're going to take a look at how it relates to binomial distribution. I kind of like, having my laptop not being the tablet at the same time, because this way I can do some typing on one side, look at the document, and then on the other side I can do the handwriting. Okay, 440. Okay, there we go. Start a new page. All right, so we'll just write down all the key information here. So x divided by 1,000 is, so x observations or x experiments out of 1,000 experiments observes 2 heads and 3 tails. Let me double check, make sure it's not reversed. Yep, 2 heads and 3 tails. Okay. So now how do we figure out what is the what is the chances of that happening? Yep. Mm-hmm. Mm-hmm. Okay, exactly. So how many people caught what's your name? I cannot remember. Matthew. Okay. He just came to my office hour to introduce his name. I'm Matthew. You asked to see me, and then I, of course, immediately forgot. I'm sorry. I apologize. That was not intentional. Okay. So so if you look at P and Q, okay, so we'll just say the P is the probability of landing on the head, and Q is the probability of landing on the tail. Okay, so it's obviously P is 1 minus Q, or you can also say that Q is 1 minus P, because P plus Q has to be 1. Okay, so what we're looking at is this particular scenario. We are looking at P plus Q, which is 1, to the power of 5. And you go like, well, that's kind of silly, okay, because 1 to the power of 5 is 1. Well, but that's not what we are really looking into. We're looking into, oh, this has, it's P to the power of 5 plus some number times P to the power of 4 times Q plus some number times P to the power of 3Q plus some number, multiplier times, P to the power of 2 and then Q to the power of 3. Oops, forgot about that. And so on until we get to Q to the power of 5. In other words, we can expand P plus Q times P plus Q, 5 times, and just rewrite everything here. But we have to figure out the coefficients. Okay, those coefficients are easy to figure out because that's exactly what the binomial theorem is about. Okay, so we know what these things are. So we can now say, oh, okay, we know what those things are. This is 5 choose 0. And this is 5 choose 1. And the next one, I mean, obviously you guys know what it is already because we do have the closed form equation in the notes. So the next one, this one is the one that I'm most interested in. And the rest, we'll just say dot, dot, dot up to 5, 5, Q to the power of 5. But this is the one that I'm most interested in because this is the one that tells me about the, if I divide this by 1, okay, that is the relative probability of 2 heads and 3 tails. Okay? So now I pick this one up and I say 5 choose 3 times P squared and Q to the power of 3. This really is X divided by 1,000. If 1,000 observations is representative of the behavior of the coin. Is that okay so far? So now since X is known, what we want to solve is either P or Q. They're basically flip sides of each other. So now what you need to do is to restate the problem as 5 choose 3 P squared 1 minus P to the power of 3 equals to X divided by 1,000, and we're just solving for P. So if you get to this point, I'll give you full credit already because this class is not an algebra class. So we are not spending the time to solve this particular equation, but instead we just have to relate how P, we have to establish the relationship between P and X. Is that okay? So does everybody understand what the question is asking and what tools we used to answer the question? Okay? Yep.
Just to emphasize.
Yep.
Q equals 1 minus pi minus p. We're coming from that p plus q is 1 from that equation, right?
Yes. Yes. P plus q equals 1. It's because they represent all the probabilities.
So
yep.
that we make substitution for q.
Yep. Exactly. So because Q is 1 minus P, so we just substitute it here. So now we only have one unknown to solve. And all the other terms are known already. Is that okay? All right. So now the question is, why did I change from 600 something to X? Well, the reason is if I have 600 something here, you can still solve for P, but it is a negative number, I think. Somebody told me that, yeah, you can solve for that, but it's going to be a negative number, which doesn't make sense, right? You cannot have negative probability. All right. So do we have any other questions about number 1? It is an application of the binomial theorem. All right. So let's move on to the second question. So in the second question, it's proof by induction. So in this case, you guys have seen this many times, haven't you? The summation of I as an index going from 0 to n, and then the term that we are summing is just I itself. So we have seen it many times. The first time we saw that was with the function g, when we talked about how to fold like 2D space into one single dimensional space. So that's when we first saw this. So it has several parts, so make sure you answer each part when it has multiple parts. So the first one is really just to work out what is f of 0, f of 1, f of 2, and f of 3. Well, that should be pretty easy, right? F of 0 is just 0, okay? F of 1 is 1. F of 2 is 3. F of 3 is 6. Is that okay? So you have to kind of put those numbers here, okay, just so that you show me that you can figure out the function or of the function of a particular value. Okay. So the next paragraph says, next, think of a way to rewrite the definition of function f, but in a recursive way. So define f using f itself. Okay. Let me see. I can just type here. Do you guys mind if I type here? Because if I type here, you will see that when you open up the document. Would that bother you? No? Okay. All right. So if it doesn't bother you, I'll just kind of write in here. F of 1 is 1. Oops. F of 2 is 3. And then f of 3 is 6. Okay. So when you look at that particular sequence, you kind of see something here, right? You can see that f of 1 is f of 0 plus 1. F of 2 is f of 1 plus 2. F of 3 is f of 2 plus 3. So there's a certain pattern to it. In other words, you're looking for a relationship between f of 3 and f of 2, but that relationship also has to hold true between f of 2 and f of 1, and then f of 1 versus f of 0. So the answer to the second part is basically to say f of n is f of n minus 1 plus n. Okay? And then defining f of k without recursion for a carefully chosen single constant k as a starting point. So we have to stop the recursion at some point. So where do you think we should stop? What is a natural point and say that one doesn't need recursion, doesn't need a recursive definition anymore? F of 0 is 0. Okay, all right. So you just add that here and just say repeat f of 0 is 0. So that k is actually 0 in this case. That's our basis. So the next part here is it leads to a suspicion that f of n is n times n plus 1 divided by 2. And then we want to use proof by induction, making use of the recursive definition of the function to prove that this theorem, meaning this part here, is true for all of n as long as n is a non-negative number. That theorem is true. So Okay, so now proof by induction is in boldface, which means you have to prove it using proof by induction. So how would you go about doing that? Yep.
Base case would be for n equal to 0, so you just plug that into f of n, show that has 0.
That would be a base case. Uh-huh.
Summation, you can show that summation is equal to n multiplied by 2.
Okay. So let's see how we can write this out, as proof by induction. And all right. So when we have proof by induction, there are two main steps in proof by induction. We talked about proof by induction when we were working on Pascal's identity. Okay, so when we prove Pascal's identity, that was the first formal introduction to proof by induction. So when we have proof by induction, there's an easy step called the base. Okay, the basis or the base step. Okay, we'll just call it is it called base case? That's it. Okay, it's called the base case. Okay, so the base case is just applying the theorem to one single number of the range of values where the theorem is applicable. Well, the range of values where the theorem is supposed to be applicable is the set of all natural numbers, 0, 1, 2, 3, 4, and so on. So it has a pretty natural end of 0. So that makes 0, k equals to 0, a very good candidate as a base case. Okay, so now we look at f of 0. Okay, we look at f of 0, and that is 0 because of the way we define function f recursively. But at the same time, we also want to look at this and ask the question, because we have to relate everything back to the theorem. So the theorem says, does it have this closed form on the other side? Okay, so does it equal to n times, 0 times 0 plus 1, the whole thing divided by 2? Yep, because 0 times whatever is always 0. So you have to make sure that you equate f of 0 to the form here, because this 0 here is the parameter, and the parameter goes into here. So this is basically applying the theorem, but only to the case when the parameter is 0. Is that okay? All right. And if you want to, you can even make it very clear and say the theorem is true when k equals to 0. So once the base case is done, then we have the induction step. So there are two distinct phases to proof by induction. The second one is the induction step. The induction step starts with an assumption. So it basically starts with an assumption of assume the theorem is true when k equals to a particular number. Okay? So we say, assume the theorem is true when k equals some particular value. We'll just call it n. Okay? That's the assumption, which is a subpart of the induction step. The second subpart of the induction step is to say prove the theorem is, I'm going to say, emphasize, also true when k equals to n plus 1. So the assumption is basically stating this. The assumption is saying f of n is n times n plus 1 divided by 2. But only for that n, okay? Only for that n, this equality is established. Now we have to show that f of n plus 1 is n plus 1 times n plus 2 divided by 2. That is what we need to show. So now we go to f of n plus 1, and then we say, well, in the end, okay, down here and all the way at the bottom, we have to show that this is n plus 1 times n plus 1, the whole thing plus 1, and divided by 2. Obviously, plus 1 is just plus 2, but I choose to write it separately because this way it fits into the format of the original expression. Okay. Okay. So how do we start with this? With almost every single induction step, regardless of what you're proving, the induction assumption is going to be useful. What do I mean by the assumption? Step 1 of the induction step. So we have to make use of that, which means we have to somehow re-express f of n plus 1 where there's a component of f of n, because that is the only time where I can use the assumption to help me with this particular theorem. Okay? But since f is recursive, that makes it really easy. Because if f is not recursive, it may not be an easy thing to re-express f of n plus 1 in terms of f of n. But since we already know that f is recursive, now we can just use the recursive definition and say, oh, okay, we know this. Is that okay? So this is because of the recursive definition. All right, well, how is that going to help me? Well, based on the assumption of step 1, we can rewrite f of n as n times n plus 1, the whole thing divided by 2, and then we just add n plus 1 here. And this one is because of the induction assumption. All right. So now we look at this and go like, looks like we can do some factoring here, okay? Because we can have a 2 divided by 2 here. Then we can have the same denominator, and then we just put this one to the top. So this part you kind of have to show me step by step, okay? Or you can skip a few steps, but just not any major steps here. Is that okay? Okay, because I just say, okay, n plus 1 is the same thing as 1 times n plus 1, but that 1 can be re-expressed as 2 divided by 2. So now we have a common denominator. So now we do factoring. So it has n plus 1 as the common factor on both sides. So we now have n plus 2, as the other part. So this part is just factoring. So this becomes n plus 2 times n plus 1 divided by 2. So from the second last step to what we really want, I think that's fine. Okay, you don't have to explain, using associative law of algebra, or 2 equals 1 plus 1. You don't have to be. You don't have to go into like extra details like that. Okay. The two parts that I think are really important and you have to show is, one, how you use the recursive definition so that f of n plus 1 is expressed as f of n and then something else. Okay, that is really important. The second part that is also important is the second step, where f of n becomes n times n plus 1, the whole thing divided by 2, because in that case you are making use of the induction assumption, which is the key of proof by induction. But that's it. This is the whole proof that I want. Doesn't have to be expressed exactly like this, but it has to have all of these components. Are we doing okay so far with the concept of proof by induction? Okay. All right. So if that is good, then we move on to the next question. Number 3. Oh, I like number 3. Number 3 says, Joe and Pat want to go on vacation together. They both read the same travel magazine that has 10 suggested destinations. Joe decides to pick 6 different destinations out of the 10, and Pat does the same thing, picking 6 destinations out of the 10. What are the chances that they share exactly 4 common destinations? Ranking is not important. Okay, so imagine there's no ranking whatsoever. out of the 10 destinations, Joe picks 6. And out of the 10 destinations, Pat chose also 6. They can overlap. They can, well, 2 has to overlap, right? Because you cannot have 12 completely different destinations when they're chosen from the same 10 destinations. But the question is asking, out of those 6, what are the chances that they're sharing 4 common destinations? This is actually a very distorted version of the lottery lotto number problem. Okay. So now the question is, in what way is it related to the lotto problem? So the way you do it is you lock one as kind of not, you don't analyze it using combinations and permutations. So you just look at, let's say Joe's, selection. You just say, okay, here is the 6, chosen destinations of Joe, okay, out of 10. So now it is kind of the same thing as you have 5 lucky numbers out of what, 40, 39? 69. So you have 5 lucky numbers out of 69 numbers in Super Lotto. Okay, same kind of deal. Okay, so then you look at Pat's selection as an individual Lotto ticket, and you're asking the question of, out of the 6 lucky destinations, what are the chances that Pat ends up picking 4 of the 6 lucky ones and 2 out of the unlucky ones? That becomes the question. Then it becomes the lotto problem again. Is that making any sense? Okay, so maybe a graphical representation is better. All right, so so I'm going to draw a picture here because I want you to understand the parallel between this problem and the lotto problem. So in the lotto problem, we have 1 to 69 as the potential numbers, okay? In this particular case, we have destination 1 up to destination 10 as all the available choices. Is that okay? In the lotto problem, out of these 69, okay, I choose 5 of them, okay? So according to the lotto website, these are called the lucky numbers. In the other problem, out of the 10, I choose 6 of these, and these become Joe's destinations. Is that okay? So this part is fixed, okay? So we basically say, okay, this is done on one side. And then we look at the other side. So with the lotto problem, the other side is you buying a ticket, okay? And you're asking, what are my chances of, matching 3 lucky numbers, okay? I'm just picking 3 as a particular example only. Matching exactly 3 lucky numbers, okay? So the calculation of this particular problem, of the lotto problem, is, so now you have to consider, out of the 5 lucky numbers, you're choosing 3. That part is pretty easy because you want 3 of the 5 lucky numbers. So obviously you're choosing 3 out of 5. But the most important part is you also have to remember you have 2 additional numbers that you have to choose from the not so lucky numbers. How many not so lucky numbers are we talking about? 69 minus 5. Okay, 64, okay? So out of 64 not so lucky numbers, you have to choose 2 of those. Okay? What about the destination problem? Well, in this case, we want, out of the 6 lucky destinations, we want to pick 4 of them so that they become common between Joe and Pat. But out of the rest, okay, the 4 destinations that were not chosen by Joe, you have to pick 2 of those. Is that okay? Are we doing okay so far? But this is not the end of the problem, because what these numbers are showing is how many ways we can have that arrangement. So when you're looking at the lotto problem, not counting the Powerball, okay, the Powerball is out of this equation entirely. So not counting the Powerball at all. There are this many possible tickets that can earn this particular prize, okay? So now you have to divide it by the total number of possible tickets, okay, to get the probability. So in this case, the total number of all the tickets is really just 69, choose 5. Pick any number, pick any 5 numbers out of 69. That is the total number of unique tickets of this particular lotto game. And this is basically it's the cardinality of omega, which is the cardinality of all possible outcomes. And this is the cardinality of the event, which are the things that you're interested in. With this one, it's the same deal. So you have to divide it by how many ways Pat can choose 6 destinations out of 10. Okay? Well, it's just 10 choose 6. So that becomes the solution of this particular problem. But what I want to show you is the parallel between the lotto problem and the destination problem. So they're really the same kind of problem, except one is very distorted because we don't have a whole lot of choices. The other one has a lot of choices, so the chances of winning is pretty low. This one has a pretty good chance. Okay, so out of 10 destinations, the chances that Joe and Pat choose the same 4 destinations is actually relatively high. You can actually plug in the numbers and find out. So is that okay? Yep.
That's just the case for one person, right? Where the other?
How about the other?
Yeah, how about the other?
How about
The other person, I mean, that's just if you choose 4, if 6 choose 4.
right?
So they're both going to do the same thing? Is that what you mean?
So the 6 choose 4 is choosing 4 of the 6 destinations that Joe has already selected. Because Joe, so without knowing what Joe has chosen, Pat can choose, randomly choose some stuff, right? So we are basically counting how many ways can Pat choose exactly 4 of the destinations that Joe has already chosen. Okay, so look at this way. Okay, so look at this as it's a room that has a divide. Okay, so you give a travel book to Joe, you give a same travel book to Pat, and then you ask each person to choose 6 destinations out of 10. Is that okay? So Joe has chosen 6 destinations, and you say, okay, this is good, Joe, and then you just hide those 6 destinations behind the wall. Okay, and now on the other side, you go like, okay, Pat, go ahead and choose 6 destinations. So Pat doesn't really know what Joe has chosen, right? So just by chance, I'm asking, just by chance, what are the chances that Pat can choose 4 of the same destinations, 4 of the same destinations that Joe has already chosen? Okay, but we already know that Joe has chosen 6 destinations. So now we just have to count. Okay, how many ways can Pat choose 4 of the 6 chosen destinations? Okay, because we want, out of the 6 destinations that Pat is choosing, we want 4 of those to overlap with what Joe has already chosen. Is that okay? That becomes our event. This is what we're interested in. So this will account for how many ways can we choose 4 of the 6 destinations chosen by Joe. But then you have two more destinations. Where are you going to choose those two destinations from? Well, it has to be from the 4 destinations that Joe has not chosen, right? Because it's binary, okay? A destination is either chosen by Joe or not chosen by Joe.
What means that if we forget Joe and whatever,
Pat.
and yeah,
Can be guy, can be gal.
and you just say, okay, choose 4 correct destinations into 6. I mean, from 6. It's still going to be the same thing. So you don't have to know if there are 10 people doing the start. Just say choose 4. I mean, what are the chances of having 4 good destinations if you pick up 6? Still, same calculations.
Okay, so I think the key is the importance of this component, right? I think this component we kind of know what it is. But this component is actually very important because once you have counted the number of ways to choose 4 of the 6 chosen ones, you still have 2 more that you have to choose. So how many ways can you choose the other 2, the 2 that are not in common with Joe's selection? This part here, 4 choose 2, accounts for that. So one way to look at it is to say, okay, what about we have 100 possible destinations? Okay, if you have 100 possible destinations, this number doesn't change because you're still choosing 6 out of the 100 destinations, and you only want 4 as an overlap. But what would make the difference between 100 possible destinations as opposed to 10 possible destinations? It impacts the second part. Because if you have 100 destinations, of which 6 are chosen, that means 94 of the 100 destinations are not chosen by Joe. And there are many ways to choose 2 out of those 94 non-chosen destinations. And that's why you can see the impact of the second component. Is that okay? Okay. So one way to look at these problems and to get a better understanding is to look at the extreme cases. What if I make the total number of choices smaller, and what if I make it really, really big? How is that going to intuitively change the distributions? Okay. So are we okay so far or not? You can also try to relate it back to the lotto problem, because the lotto problem is usually more commonly understood because the process is really well understood. Is that okay? Yep.
So that's the final answer we could just
The final answer is this.
Yeah.
Yeah, that is the final answer. Correct. All right. So that's question number 3. And here comes question number 4. Question number 4 is proof by contradiction, which we first encountered when we talked about resolution stuff, okay? So in this case, it is a template, okay? So I'll have to read this question really carefully because I think last semester there were a lot of questions about, okay, what is it really asking me? So use proof by contradiction to show the framework of showing a theorem that has this particular template. In other words, the theorem that you want to prove involves something, if and only if something, okay? But what exactly is rho? What exactly is phi? I don't know, and it does not matter, okay? It just has that format. Is that okay? So the theorem that we want to prove is some kind of if and only if, okay? One side is represented by rho, the other side is represented by phi. Exactly what they are is not important to me, okay? And the statements assumed true are contained in psi. So psi is one gigantic expression that says all of these things are known to be true, okay? Now, if all of these things are known to be true, can we conclude that rho is true if and only if psi is also true, phi is also true? That is the question. is this a theorem of that? Does it follow? Is that okay? More or less, maybe? Okay. So if I were to reformat the question, it is really asking this. I know you cannot see the tablet because I need to write this first. Rho if and only if phi. Okay. There we go. The question is asking this. Does psi, which is one gigantic expression of some kind that represents everything that we know is known to be true, does that imply this thing here, which is rho if and only if phi? That's the question. And we want to prove it. But we want to prove it using proof by contradiction. So is that okay? I mean, does everybody understand what the question is asking? Okay. All right. So what do you do when you want to prove by when you want to use proof by contradiction? You start with negating the theorem. Okay. So if the theorem is rho if and only if phi, then the negation of the theorem is really just the negation of rho if and only if phi. Well, if the answer is that simple, I wouldn't have asked it. Okay? So let's read the question a little bit more. There's no way to actually derive the proof itself before, because we don't know what is rho and what is phi. In the following space, specify the framework as much as possible, just knowing what is given in the question. In other words, work out the proof as far as you can until you actually need to know what the Greek letters are representing. Okay. So what it really is saying is, well, what is that? So you have to say this is the negation of P implies, rho implies phi, and phi implies rho. That's the definition of if and only if. And then you say, well, let's get rid of all the implication. So this becomes not rho or phi. The other side becomes not phi or rho. Is that okay? And what is that going to become? Let's see. I'm just trying to figure out what is the best way to do this. Let's do De Morgan's law. Okay, we'll distribute the negation. We'll distribute this negation to the inside. So now it becomes the negation of not rho or phi as one thing, but we have to change the conjunction into a disjunction, or the negation of not phi or rho. Is that okay? That's De Morgan's law. And now we apply De Morgan's law again into the inside of each or. So the first one becomes not rho and phi. The second one becomes not phi and rho. Okay. Oh, I forgot one negation. No wonder it doesn't look right. There we go. Okay. So now we can cancel out the double negation. So one side becomes rho and not phi, and then the other side becomes phi and not rho. And that's basically as far as you can push without knowing what each Greek letter is representing. Huh? That's it. Yep. This is all that you can do. Because unless I tell you what is rho and what is phi, you cannot prove that this is a contradiction. Because by itself, it is not a contradiction. Yep.
Could you turn that into a CNF, then take the conjunction of that with our original set of theorems, and at that point we would have to solve?
You can turn it into a CNF, but the CNF is not resolvable. It's not resolvable because you cannot tell whether you can cancel out things until you know what is rho and what is phi. Oh, yes. So yes. So basically, you have to say psi and rho and not phi. Oops. Or phi and not rho. This has to be false. So show this is false. So that becomes the full explored term of the whole thing. But if you just get to re-expressing the negation of the theorem to this form, I'll still give you full credit.
It's not CNF though.
Hmm?
It's not
Nope.
CNF.
The question did not ask about CNF.
Doesn't need to be CNF to
Nope.
prove by contradiction.
Nope, nope, nope. Because proof by contradiction is a concept independent to resolution. It is the resolution mechanism that requires CNF. But in general, you can apply proof by contradiction without using CNF or resolution. Okay?
Why do we get rid of implication though?
Huh?
Why do we get rid of implication then?
We get rid of, well, this way, we reduce everything down to disjunction, negation, and conjunction. Okay, do you guys want to see an example of something that has this particular format? Okay. Let me see what question 5 is, before I talk about that one. Oh, question 5 is easy. Question 5 is, this is a CNF question. So question number 5, definitely wants to convert this expression into a CNF. And then the proposed theorem is down here. There are two proposed theorems. So one is this one, and one is this one here, and you have to use a resolution to prove both of those. So question number 5 is fairly mechanical. There's a whole bunch of derivation to turn everything into a CNF. But once you have the CNF, it really is just resolution. Okay, match up a variable with the negation of a variable, do a concatenation of the rest of the stuff, and then put it at the end of the whole thing, and then see if it resolves with anything else, that sort of thing. Okay, so I think we can spend some time on proof by contradiction, because it's more conceptual with that particular question than it is mechanical with this particular question. So one thing we can prove, okay, some of you have seen this already. For all P, A, B, and it works in many different domains, but I'm just going to say natural numbers, okay? So if P, A, and B are all natural numbers, we know this much, okay? We know that P equals to AB implies, this is only implication, it's not a if and only if. Yep. Oh, okay. Can't see it. Okay. It implies, it's still okay. It is not in the same format of if and only if, but it is still useful in the sense that it shows how to prove by contradiction. So I think it's still useful. It's just not using if and only if. So in this case, P equals AB implies A squared is less than or equal to P, or B squared is less than or equal to P. Okay, one more close paren, there we go. This is our theorem. So the first question is, what are we talking about? Okay, so the first thing says, P has to be the product of A and B. So if you choose P to be 16, A to be 5, and B to be 3, then it automatically is true, because P equals to AB is false in that case, and because this is an implication, if the first part is false, the whole thing is true. Is that okay? So we only really pay attention when P really is a product of A and B. Is that okay? All right, so knowing that P is the product of A and B, okay, in simpler terms, it means A is a factor of P, B is a factor of P, okay? And what it really is saying here is at least one of the factors of a number is less than or equal to the square root of that number. That's all it's saying in English. Is that okay? Okay, let me say that one more time. When you look at a number, as the product of its factors. Okay? At least one of the factors is less than or equal to the square root of the number. Okay? Let's look at some examples. Hmm?
Why is it or? Why is it not and?
It is or, it's not and. Okay, so let's look at 12. Okay, so 12 is 3 times 4, right? And in this case, 3 is less than or equal to the square root of 12, but 4 is not, right? Because 4 squared is 16. So we know that 4 is not less than or equal to the square root of 12. But 3 is, because 3 squared is only 9. So we know 3 is less than or equal to the square root of 12. Is that okay? You can also look at perfect squares, like 9. 9 is 3 times 3. So in this case, 3 is less than or equal to the square root of 9, and or 3 is less than or equal to the square root of 9. That is still true. A disjunction means at least one side has to be true, but both can be true at the same time. Is that okay? So I bet you cannot find a number where both factors are greater than the square root of the number itself. Okay? But just because you cannot find an empirical example doesn't mean it is universally true. Maybe you haven't spent enough time to find it. Right? So now the question is, how do we prove this? This is one of those examples where a direct proof is actually a little bit harder than proof by contradiction. Yep. Yep. So we negate it first, okay? So because we have already talked about quantifiers, okay, so we have to look at quantifiers or negate how negation apply to quantifiers. So the negation of the theorem is now the negation of the whole thing. Okay, I'm going to be super lazy here because I can use this. Not enough space. Okay. Cancel that. Move this one over here. There we go. Yeah. Take that. Okay. So the negation of the theorem is this. So the first thing we do is to go like, well, we are negating a for all, okay? Actually, I forgot to copy the for all here, okay? But we're negating a for all. So when you negate a for all, you can, okay, so I forgot about this part here. So you can now say, there exists a P, oops, okay. There exists P, A, B in the natural number set such that it is the negation of the following. So now you move the negation into the predicate. The whole thing. You're negating the entire thing. So a squared is less than or equal to p, or b squared is less than or equal to p, extra paren, and we need to close this one and then close that one. There we go. Okay. So now you look at this negation. Okay, let me show you which negation we are talking about. So now you look at this negation and say, okay, we need to negate this whole implication. When you negate an implication, you have to first get rid of the implication, turn it into negation and or. So now we say there exists P, A, B in the natural number set such that it is not true that the negation of P equals AB, and then you turn this or into the implication into or, and then we have a squared is less than or equal to p, or b squared is less than or equal to p, close, 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 close. There we go. Okay. Are we still doing okay so far? Okay. So I just got rid of the implication operator, that's all. So now we say there exists P, A, B in natural number set. So now I'm going to apply De Morgan's law. So as it turns out, De Morgan's law is really handy because as long as you have blah, 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 or blah, 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 or blah, 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 okay, you can apply De Morgan's law once and turn and negate every single term and then change all the disjunctions into conjunctions, okay? So that turns out to be super handy because now we can say not P equals AB and not A squared is less than or equal to P and not B squared is less than or equal to P. So we have fewer parentheses to deal with this time. So now we continue with this. There exists P, A, B in the natural number set N. Negation of a negation cancels out, so we only get P equals to AB left. And A squared is greater than P, right? The negation of A squared is less than or equal to P is the same thing as A squared is greater than P squared, greater than P. And same thing with B, B squared is greater than P. Okay, so now we look at this and go like, now it's algebra. Okay, we have done everything that we could with Boolean algebra. Now it's really just algebra itself. So what we do is say, if P equals to AB, then we know, okay, this is actually bidirectional. So we say, P squared is A squared times B squared. Is that okay? We just multiply both sides by itself. So we have, basically we are just squaring both sides. Is that okay? Okay. So if you combine this fact here, P squared is defined to be A squared times B squared, okay? Doesn't that conflict with the other two conditions? Because if you combine these two, okay, so if you combine these two, this is implication. We know that A squared is non-negative. We know B squared is non-negative. We know P is non-negative. We know because they're all natural numbers. So because they're all non-negative, using inequality, you know that when you multiply A squared and B squared together, that should be greater than P squared. Because A squared itself is greater than P, B squared itself is greater than P, so when you multiply the two bigger terms, that product should be bigger than the product of the smaller terms. Is that okay? So now you have this kind of weird condition here of a particular expression equals to the other expression, but at the same time greater than the other expression. That cannot be true. You cannot find such an example with natural numbers. So the whole thing is now false, okay? So this whole thing is false. There's a contradiction. So this is kind of like a full-blown example of proof by contradiction. First using Boolean algebra to solve everything down to this point. Then we use regular algebra and inequality to solve for the contradiction. So is that okay? This is one of those few, theorems, not so few, but this is one of the theorems where the indirect proof using contradiction is way easier than a direct proof. You basically just say that, well, let's just say that the theorem is false, and then you show that it is not possible. Oh, that reminds me of one thing. That reminds me of you asking me to prove Dijkstra's algorithm finds the shortest path, because we're going to prove that by contradiction. One more exercise of proof by contradiction. But remember, graph theory and Dijkstra's algorithm is not in exam 2. So no need to worry about the details of that algorithm. But I want to show you how that is proven. Okay. So what we want to do is to say, if you have a vertex V, which is a vertex of question, and then you have a destination over here, and you say, well, the Dijkstra's algorithm finds a path, but it's not optimal. Okay? Well, that means there is a different path that is optimal. Is that right? Is that okay? But at some point, now the other path may be entirely different, but it can also overlap with this path to a certain point. Is that okay? So we'll just say that they are the same up to a certain point. So the two paths basically converge. They're the same up to here, and then the actual shortest path is here. Okay, maybe I should use dotted lines. Okay. So the dotted line represents the detour to the actual shortest path. Are we doing okay so far? Okay. So the question is it possible for Dijkstra's algorithm to find the non-optimal path but not find the actual shortest path? Is that okay? I had the proofs in my head just moments ago. I just need to remember how I approached that. The question has to do with this point here, because when we're at that point, okay, so when we're at this point, let's say these are the two vertices that are both going in this direction, okay, so we have to give these two guys names. So we'll name one W, and we'll name the other one Y, okay. All right. So at this point, because this vertex, we need to give that one a name too. So we'll name it, X has not been used, so we'll name this one X. So X has to be in the set Q at one point or another, okay? Why? Because everything that is, that has a known path to the destination has to be in the set Q at one point or another. And that has to do with the algorithm adding all the incoming vertices to Q when you explore something from Q originally. And we know that the destination itself was the only element in Q originally. So that means we know X has to be in Q at one point or another. So if X is in Q at one point or another, it has to look into W and also Y. Is that making any sense? Okay. So when you look into W and when you look into Y, okay, I think the key is this has to be a direct edge here, not a path. Okay, there we go. That makes more sense, and these two are this is also a direct edge. So this is an edge here, this is also a potential edge. There we go. Now it makes more sense. So when these two are expanded, then W is going to be in Q at one point, and Y is going to be in Q at one point. Okay? It doesn't matter which one you pick out of Q first. So let's say you pick W out of Q first. Okay? So the edge V, so when V goes through W to D, it is the non-optimal path. Okay? But let's say you explore that first, and then you update the L value of V accordingly. But you don't, at some point you will have to pick Y out of Q, because the algorithm does not terminate until Q is empty. So we know that Y has to be picked out of Q at some point. When it does, Y has to look into all of its incoming edges. Vy is one of the incoming edges. When that edge was explored, we would have found that the path, or the length of the path from V through Y to D is going to be less expensive than the path of V through W to D. And then we would have updated, according to the conditional statement, we would have updated, erase this edge from E prime, and then add this edge into E prime. Okay? But what if we explore these two vertices in the opposite order? In other words, we first explore Y, and then we explore W. Well, if we first explore Y, then we would have recorded the actual length of the shortest path as L of V to begin with. Then when we explore W, the length of this path, the path of V through W to D, would have been more costly, and we would not have gotten into the conditional statement to record VW as an edge in E prime. So that shows that this case is not possible. Okay. Yep.
What if we don't have a direct edge from V to W and from V to Y? What if the connection between those two is another path containing arbitrary...
Between which two? Between V and W or between V and Y?
Both of them. Relax the assumption that there's a direct connection between those two points.
Right.
There's no path.
I think there's a way to reduce it to the same argument at some point. It has to be, there has to be one last edge that you connect to. I think I know how to argue with that one. So here's D, okay, and here's X, and then Y is along this path here, which is actually part of the shortest path, and then V is here. This is the last edge. So VY is still the last edge that we need to that needs to be considered, and then W is the last one here. The same argument will still have to apply, even though in this case there's a path, not a single edge, between X and W and between X and Y, but the same argument still has to apply because it has to choose between W versus Y. And both have to be in Q because they are both reachable from the destination, so they have to be in Q at some point. But everything in Q has to be expanded for each loop because the algorithm would not terminate otherwise. So the same argument would still apply and say that if you explore W first, okay, which is the non-optimal path, then it's okay. You will still find this edge initially. But at the time when Y is expanded, because Y has to be expanded at some point. So let's say Y is expanded later, then we will have discovered this edge is actually completing a shorter path from V through Y to D. X becomes irrelevant in this case. Is that okay?
So we're not actually proving that we get the shortest path. We're just showing that what we end up with does not diverge from the shortest path.
Yes. So the key is not even whether W and Y are converging to the same vertex. It's just that they are both reachable from V, and they both have to be explored at one point because one is on the shortest path, which means it is reachable to the destination. So it has to be explored at one point or another. So it's still proof by contradiction because I'm assuming that we found a non-optimal path, and then we show how it is not possible. So that is still proof by contradiction in terms of technique. And then in this case, what do you think is the psi? Remember, I used psi as a Greek letter to represent everything that is known to be true, the basis of all the proofs. What do you think is the most important part of psi in this case? The algorithm itself. The logic of the algorithm is where the psi is coming from in this case. So you're basically saying the algorithm as it is specified and the negation of the theorem, which means we found a path in E prime that is not optimal. That is causing a contradiction because it could not have happened. So that is still using the technique of proof by contradiction. So are we good so far with that proof? So anytime you want to prove the correctness of an algorithm, if you look at the algorithm, it's long, it's complicated, has a lot of stuff in it, focus on the conditions first. It is usually the conditions, particularly the conditions of a conditional statement, and also the condition of a loop, that is going to be one of the key components of your proof. Because those are the things that basically help steer the algorithm to go one way or another way. So are we good so far with the next exam? So it's going to be next Wednesday, open book, open notes, anything that's either printed or handwritten, you can bring it to the test. I don't think you will need a calculator because because with all the questions that involve calculation, I will say if you show me the formula, okay, the expression, in a particular way, I will count it as a correct answer. So you don't have to actually give me the actual numbers in the end. So it's the process of how you derive the equation that is important. It's not the final number that is important. Yep. We do not have class on Monday. That is correct. But I will, answer email, on Monday as if it is a regular day. So this way, if you have questions, on Monday, you can ask me. Question? So predicate calculus is excluded from exam 2. So is Dijkstra's algorithm. A star is also excluded. We have just gotten started with A star, right? All right, I'll see you guys next Wednesday, which is going to be the day of the test.
This is my first time like writing in the terminal and stuff like that. I've never had to do that for other classes, so I'm still